Okay, some more glancing collisions we can look at. What if we have a ball heading towards a wall and it bounces in this direction here? So let's give this an m value, and we'll call this one here a v value here. And of course we've got m here, and then we still have the same velocity here. So we're going to assume a perfectly elastic collision with the wall here, and it bounces off. Okay, and we've got some kind of angle, and it doesn't matter how we reference it. Let's say we reference angle theta here and angle theta here. Okay, so we know that this is a glancing collision because it's not head-on collision there. Okay, and then here's our angle. Okay, so we have a velocity vector here, and we'll need to break this up into x's and y's again. So we have a vx, and then we'll have a vy. So to get this, okay, I'm going to just draw a simple triangle here. It always helps me to draw triangles here. So here's our angle theta here, okay, and here's our hypotenuse. It looks like the y direction actually is governed by the cosine this time. So vy is going to be v cosine of theta. And then our vx, which will be this one here, is going to be vx equals v sine of theta. Okay, now as I look, vy is parallel to the wall here, so vy does not have any effect on the collision here. So we're actually looking at vx here in order to kind of figure out what's going on here. Okay, so if I want to calculate the impulse, okay, of this collision here, so I'll say impulse, okay, that's going to equal the mass of the ball. Okay, and then we've got a positive, v sine theta here, and when it bounces back off the wall, here I'll kind of draw the triangle there as well. Okay, it looks like we're going to have then a negative, v sine theta minus a v sine theta, because the beginning velocity in the x direction is a positive v sine theta, and afterwards it's a negative. So that would be equal to impulse. Okay, now of course impulse does equal force times time. So if I wanted to know the force of the wall during that collision, I can just one more time, force is equal to impulse divided by the time. So whatever I get by this calculation here, I can find the force. But ultimately we would then realize, okay, that our force vector during the collision is pointing in this direction here. So when the ball collides, the force vector is just going to be pointing there. And our y direction here is completely unaffected, okay, by what's going on. So our vy is still v cosine theta and does not change at all. So that's another good use of a glancing collision. And they're useful in lots of ways. Let's say I've got a car moving in this direction. Let's draw a box going this way. Okay, and then another car going in this direction here, and they end up colliding with each other. We have to consider the fact that this one has a vx only and no vy, and this one here has a vy only and no vx. So when you do the momentum on this one, and depending if they collide and stick to each other or not, we will have to keep, we'll have to do momentum x completely separate from momentum y, and then when we're done, we would have a velocity going off in this direction here. We would have to Pythagorize and inverse tangentize that when we're done to get our final velocity vector, because we'll have a final velocity in the x direction, we'll have a final velocity in the y direction. So that's kind of how you would do something like that if two objects are colliding like that. All right, so that's how glancing collisions work, and that's it for Chapter 6, which is on momentum and collisions.